Here, we're going to discuss solving systems of linear equations using inverse matrices. So everything is going to be predicated on this equation AX equals B, where A is going to be the coefficient matrix of my system. X is going to be my variable matrix, so the variables that are in use in my system. And then B is going to be my constant matrix, so that's going to be my constants over here. Okay, so what that will look like in this specific case, A is going to be the coefficient matrix. So it's going to be a 2 by 2, and I'm just going to grab the coefficients since each of these equations are already in standard form, xy equals a number and xy equals a number. So this first column will be the coefficients of my x variables, so 3 and 2. And the second column will be the coefficients of my y variables, so -2 and -1. X is going to be my variable matrix, so I'm using the variables x and y, so x and y. And B is going to be my constant matrix, so it'll be this column over here that has just my constants. So in this case, 4 and 3. So given the equation AX equals B, I'm taking these matrices that I have and I'm setting up this nice equation. 3, 2, and -2, -1 multiplied by xy, and that equals 4, 3. Now, if you're wondering where this came from or why this works, let's go ahead and do the matrix multiplication here. So we're going to have 3x minus 2y equals 4. Hey, well that's just this equation right here. So the next one will be second row, first column, so 2x minus 1y equals 3. So 2x minus y equals 3. So this uses a combination of matrix multiplication with our concept of equivalent matrices and setting up nice equations. So what's going to happen now, I have this matrix multiplication problem, and I'm going to multiply both sides on the left by the inverse of my coefficient matrix. So what that's going to do is the inverse and the original matrix will multiply together to become the identity matrix 1, 0, 0, 1, which then will multiply together by this xy, which will of course just leave me with xy, and that will equal then the solutions. Okay, so let's see what this is going to look like. So let's first find the inverse of our matrix A, our coefficient matrix. So the first thing we need to do is to find the determinant, so 1 over the determinant. So 3 times -1 is -3, minus, and then 2 times -2, so really we're going to say plus 4. And that's going to be multiplied by, so switch the order here, so -1 and 3, and then switch the signs here, so 2 and -2. So what this looks like is the inverse of A, so this is going to end up being 1 over 1, which really is just 1. So I'm multiplying all the terms by 1. So nothing is changed. So here is going to be my inverse. So that's my inverse of my coefficient matrix. So I'm going to take both sides of this equation and I'm going to multiply it on the left by this matrix right here. So let's kind of see what that's going to look like. So I'm going to set it up. -1, -2 with my 2, 3, and then I'm going to rewrite the rest of this stuff. And now that equals, so I'm going to multiply it on the left again. And I'm multiplying it by my constant matrix here. Okay. So I know that when I multiply these two things together, this is going to give me the identity matrix. And when I multiply that by xy, I know that's just going to give me xy. Okay, so the point of all this on the left side is just to get rid of this, and it just gives me x, y. So ultimately I'm going to be using equivalent matrices. So what about on this right side? When I do this multiplication, so negative 1 times 4 is negative 4, plus 2 times 3 is 6. And on the bottom, negative 2 times 4 is negative 8, and 3 times 3 is 9. So that ends up being 2 for the top and 1 for the bottom, which means the solution to this system of equations, x equals 2 and y equals 1. So it's the ordered pair 2, 1, and 2, 1 then will be the solution to this original system of equations. So I know that seemed like an awful lot of work, but once you get comfortable doing this process, this is actually a very quick way to solve these systems.